Hello everyone and welcome to this sixth lecture in this course. There is introduction to remote sensing, and in this particular topic we will be discussing the interaction mechanism of electromagnetic radiation with the objects which are present on the ground, especially vegetation, bare soil, water bodies, and their response curves, spectral response curves, which we will see how these curves of different objects at different wavelengths they behave. For example, when there is a when this radiation, solar radiation interacts with the target, an example here of vegetation, then there might be reflection from the vegetation, there might be some absorptions of solar energy by the plants, and there might be transmission. So, all these three things will keep occurring, whereas leaves, especially if they are having chlorophyll content, then they will have a different response in a visible part compared to the infrared channel and so on, as we can see in this small spectral curves of three types of objects which are shown here, and these are more or less standard spectral curves, wavelengths on the x axis and reflection in percentage is given in the y axis. But we see that the bare soil, which shows the maximum reflection around 1.4 to 2.6 micrometer, and whereas the vegetation, which is very important to notice, that suddenly around 0.7 it jumps and it shows the very high reflection compared to other parts of EM spectrum, whereas the water only shows in a very small part of EM spectrum some reflection, and then there is a sort of complete absorption. So, all these reflection, absorption and transmission phenomena will occur together, and different objects in different part of EM spectrum will behave differently, as we are seeing here. We will see these things in much more detail. That radiation that is not absorbed or scattered in atmosphere can reach and interact with the earth's surface. And so remember that when the solar radiation is coming, some portion of that is absorbed within the atmosphere, but remaining part may reach to the earth surface and can interact with the objects which are present there. And the three forms of interaction can take place when the energy strikes, or it is the incident upon the surface, and these three are absorption, which we have discussed, transmission and reflection. So, the total incident energy will interact with that surface in one or more these three ways. The proportions of each will depend on the wavelength of energy, that is very important, and the material and the conditions of the features. Conditions of the features means if the vegetation is very healthy, having high chlorophyll content, it will behave differently, but the same vegetation, if it is not having, it is drying up or having some disease, it will behave differently in different part of EM spectrum. So, that is why it is mentioned is the condition of feature. Now, this radiation or interaction, there might be two ways, that one is this reflection, and there might be a reflection by the man-made surfaces or some natural surfaces, and which we call as a specular reflection, and there might be a diffuse reflection which may be because of vegetation, maybe bare soil, some rocks and other thing. So, these will affect the signatures or their presence in the satellite images at different bands. So, two types of reflection which are observed, mainly which are two extreme ends in the way energy interact and reflected back. One is specular reflection, maybe from the roads, maybe from a calm water surface and so on, whereas the diffuse reflection may be from vegetation and other places. So, specular reflection, the maximum energy is reflected back, whereas diffuse reflection some, and it is scattered all around. So, when a surface is smooth, we get a specular or a mirror like reflection, where all or almost all of the energy is directed from the surface is in the single direction. And whereas diffuse reflection occurs when the surface is rough and the energy is reflected almost uniformly in all directions. And most of the earth features which are not really perfect specular reflectors or neither diffuse reflectors. So, most of the features falls in between of these two categories, and whenever a particular target reflects specularly or diffusely or somewhere in between depends on the surface roughness of the feature in comparison to the wavelength of incoming radiation. And the example here is that if wavelength is much smaller than the surface variation or the particle size that make up the surface, diffuse reflection will dominate. For example, the fine grained sand especially present in the desert areas would appear fairly smooth to long wave microwaves, but would appear quite rough to the visible wavelength. So, it depends the same surface, but depends on the wavelength, in which wavelength or in which part of EM spectrum you are looking or which band of the satellite image you are looking. The same object may look very smooth or in larger wavelengths, but may look rough in visible wavelengths. Similarly, the leaves, plant leaves, the chlorophyll strongly absorbs radiation in the red part and the blue wavelengths, but reflects green wavelength, and that is why we see in the visible part, when that is why we see vegetation, healthy vegetation generally green, because the red portion and blue portion are absorbed, whereas the green is reflected. And leaf appears greenest to most of us in summer when chlorophyll content is at its maximum, depending on the season of different areas in the country or world over, whereas in the autumn when there is a less chlorophyll content, so there is a less absorption and proportionally more reflected of red wavelength and making leaves appear either yellow or red, and yellow is a combination of red and green wavelengths. So, when chlorophyll is less, then the green is not reflected, and whereas red is reflected or yellow or green is reflected, and that makes us yellow. Similarly, in this healthy vegetation act as a excellent diffuse reflectors of near infrared bands and infrared wavelengths, and that is why though in our eyes it is different, but in infrared radiation, in infrared bands the vegetation is having maximum reflection. So, our eyes were sensitive to basically to near infrared trees would appear extremely, if at all these our eyes would have been, but we are having sensors in near infrared, and therefore we get very high reflection, and in fact measuring and monitoring the near infrared reflection is one way that scientists can determine how healthy or unhealthy vegetation may be. And this people exploit especially for crop estimations or health of a forest area and so on and so forth, that if you are getting very high reflection through infrared channels of an area which is completely vegetated or having some agricultural crop, we can assess that that area is enjoying good growth of plants, or a good chlorophyll content are present in the leaves. But if this near infrared reflection is less, then there might be some problem with the plants. As you can see that these are the plants seen through the infrared channels, and they are showing very high reflection, whereas the roof of a house or windows are showing very low reflection. So, this property of plants we exploit in our remote sensing data, and we use the combination to create certain products which we can apply for different kind of applications. Now, we take the water, then the longer wavelength visible and near infrared radiation is absorbed more by water than the shorter visible wavelength. As you saw earlier in the spectral curve of water, in the shorter wavelengths there is some reflection by the water, otherwise in the longer wavelength it is completely absorbed. And that you can see here also that this is completely absorbed. Thus water typically looks blue or blue green due to stronger reflection at these shorter wavelengths and darker if viewed in red and infrared. So whenever we see the infrared images in which the water bodies is present, generally if water is pure it will completely appear black or dark because of there is no reflection in that part of EM spectrum. Whereas if we look the visible part or shorter wavelengths, we might see some reflection of water, especially in the blue portion of EM spectrum or blue or green. That is why we see generally water, though you know that pure water does not have any color, but these colors are coming because of reflection in the different part of EM spectrum. And if there are suspended particles present in this upper layer of water body, when this will allow better reflectivity and a brighter appearance of the water. So if it is not pure, like here suspended particles are shown here, then you will get a larger reflection in these parts, and same maybe little more in the red, and infrared maybe less. So this kind of changes will occur when we are having suspended sediments, or we also call it turbidity present in the water bodies. And this is the example is shown here, and this is the delta which is shown here, and this Ganges and Brahmaputra basically are coming here, Sundarban delta, and they are bringing sediments and mixing with this Bay of Bengal. And what is happening because of this presence of suspended particles and due to that high reflection in especially in the blue part of EM spectrum, and therefore in a Landsat TM near real color images we see a blue portion, and that directly indicating high concentration of sediments present, whereas when you do not have much sediments present, then hardly you are having reflection, and therefore they are in true color images they are appearing as black. So this is how interpretations can be made of satellite images, whereas the green is of course vegetation, and there are water bodies, inland water bodies which may not be having much suspended particles, and therefore they are appearing black. So the quality of water can also be assessed through such interpretations of satellite data. As I have already mentioned that suspended sediments which shown here can be easily confused with the shallow but clear water, since these two phenomena appear very similar. That means that if water conditions are very shallow, then the bottom of say there is a lake, it is very shallow, then the bottom of the lake will also reflect. So one should not get confused with the that kind of thing, that the shallow the less column of water may also reflect, whereas at the same time the suspended particles can also reflect. So one has to ground check whether this is because of suspended particles or shallowness of a lake or water body. And in normal conditions one may find the algae and other other things which are present in the water, which will again, because algae might be having chlorophyll. So chlorophyll in algae absorbs more blue wavelengths and reflect green, making the water appear more green in color when algae is present. And this type of growth of algae, especially in sea water, and detection of these algae is used to find certain type of fish which may prefer that kind of algae. So this is how remote sensing can be employed to find a certain type growth of algae, and then associated fish might be there. And sometimes the undulations or ruggedness or topography of the water surface, that is if it is not standstill water, rough, or depending on rough or smooth or floating material etc., can also lead to complication for water reflected interpretation due to potential problems of specular reflection and other influences on the color and brightness. These curves is spectral curves of three main very standard curve which we have seen already in a small portion, that generally the water will reflect only in the shorter wavelength near 0.4 to 0.7, 0.1 or 2, and then it is completely absorbed. So only in the first part of visible part of EM spectrum, and maximum you would see around blue, that is why pure water in a color composite may appear as blue. Whereas bare soil, it increases very smoothly, and in mid infrared it reaches to the maximum, and therefore you do not see much reflection of bare soils in the early part of EM spectrum, especially visible and near infrared. Whereas the vegetation is having altogether different, there is a absorption of vegetation, but starting from 0.7 to about 1.2 or 1.3, it is having the maximum peak, where you get the maximum reflection by the healthy vegetation, green vegetation, and if there is a the vegetation is not healthy, then there might be a shift in this curve, and that the curve may shift towards the left. So we also use this to find out whether vegetation is healthy, enjoying good health, a chlorophyll content is normal or abnormal if there is not high reflection which one is getting in near infrared. So by measuring the energy that is reflected or emitted by the targets on the earth's surface over variety of different wavelengths, we can build up a spectral response for that object. These are the standard generalized spectral curves of three different types of earth objects which you are seeing here. By comparing these response patterns of different features like here soil, vegetation and water, we may be able to distinguish between them. As you can see that all three different objects are showing completely different signatures or curves or behavior in this part of EM spectrum, especially in visible, near infrared and mid infrared. As we have seen that the like water and vegetation may reflect somewhat similarly in visible wavelengths, but are almost always separable in infrared. So in one particular channel or in band you may not differentiate certain objects, two objects, but if you start looking the different channels, you will find a completely different signatures or their pixel values completely different in different channels. A spectral response can be quite variable even on the same target type and can also vary with the time, especially about talking about the vegetation. So the same vegetation may reflect differently in different season of a year. So understanding of these factors which influence the spectral response of features of interest are critical, and that makes once we start understanding these spectral curves of different features, especially in mineral exploration or in other mapping, then we can make our interpretation much more reliable. Here a few more curves have been also added, and then corresponding bands or channels of different few satellites are also shown, mainly spot and Landsat. So let me go one by one. That when you are having clear water lake water which is standstill, clear means you do not have the suspended particles, you may not be having any algae or any chlorophyll content, then the maximum reflection will come around 0.6 micrometer, and then there is a total absorptions in beyond this range. Whereas if water is turbid, that means there is a turbidity, there are suspended particles are present, then the reflection may continue even up to 0.9 or very close to 1 even in near infrared part. Similarly, in case of wet soil or dry soil, this behavior of these soils, depending on the content of water, they may show completely different reflection curves. As we can see here, that initially they are showing like dry soil will always have more reflection as compared to wet, and there are some portions where you are having the maximum difference. So, two examples are shown: 5% water dry soil, and which is we consider 20% wet is a one. And so, as soon as the soil becomes wet, it is showing a less reflection in almost in the between 0.4 to 2.4 micrometer throughout this visible near infrared and mid infrared region. Whereas vegetation is if it is healthy vegetation, it will show very high reflection between 0.7 to 1.1 or 1.2 micrometer, and in between also there are some other peaks are there, but otherwise this is the standard one. So, when initially when the Landsat 1 was designed, that is we also called as ERTS, and the sensor MSS, at that time these bands had the same width and a continuous fashion. So, like 0.45, 0.4 to 0.5, 0.5 to 0.6 likewise. But later on it was realized that such approach is not good, and therefore wherever for whichever phenomena which we were looking to discriminate, or the objects which we wanted to discriminate very easily, so then these bands and their width were changed. Like in case of Landsat TM bands, as you can see that Landsat 1 and 2 are in the blue and green part, 3 is the in the red part, then 4 is having much more larger width compared to 3, and 3 is having very thin band compared to 1, 2 or 4. And then because of in between nothing was kept, because if one is looking the vegetation, then the band 4 is the best in that sense. If one is looking for water bodies and other things, then 1 and 2 or even 3 up to 3 are good. So, then a large gap in EM spectrum was left, and then the fifth one was kept here to see the differentiation, and especially another peak of the vegetation, and then again band 7 was kept here again to catch the peak of wet soil, dry soil as well as the vegetation. But in between 5 and 7 the large gap was left. Band 6, which is missing here, falls in the thermal infrared part, that is why it is not shown here. Whereas in case of SPOT, which was a French satellite, multispectral bands which are quite similar to the Landsat TM bands, but there is some shifting of band 1. Instead of starting from 0.4 or 0.45, it really started at 0.5 to 0.6, and a very small gap between band 1 and 2, but there is some gap between band 2 and 3. So, later on people realized that based on these spectral curves, instead of having continuous bands and having uniform thickness bands, it is better to have bands based on these spectral curves, where we can discriminate or record these different objects which are present on the earth in a different way, rather than having uniform slicing and same size of or a location or a continuous slicing. So, that was a intelligent move later on, once people realize through the experience of Landsat MSS. So, this brings to the end of this particular topic about how this solar radiation interacts in different part of EM spectrum with different objects which are present on the surface of the earth. We mainly focused on the water bodies, bare soils and vegetation, and how these absorption phenomena and atmospheric windows which are available, and how different satellites and their sensors have been designed and kept at different locations, so we can capture all the important features or objects which are present on the surface of the earth. Thank you very much.